The last topic in this series is something known as the power factor correction. Here we have, let's say we have an inductive load, that means it's a lagging power factor. So that means that the angle between the voltage and current would be lagging the voltage. And if we use a capacitor in parallel with it, that means we can reduce the angle between the uh, current and voltage of this whole load. So here by power factor correction we mean that we have an original inductive load and then we have a capacitor right next to it in parallel and we have an improved power factor. This is an optional topic. It's actually covered in a lot more detail in some other power um, courses, but here this is an introduction. So here I mean it's only for your, because it's given in the book and it's part of your course, but it's a kind of an optional topic. If we want to figure out the value for the capacitance, we have to figure out the p tan theta 1 minus p tan theta 2 divided by omega v square. I mean, before going into this example, let's take a look at what is the effect of power factor. Let's say we have a source and we have a line of 1 plus j ohms and we have a 22 kilowatt unity power factor load. So power factor is unity, cos inverse is 0, angle is 0. That means a purely resistive load. So I can just write power factor equals to P over apparent power, that is 1. So I can write 22 kilowatt, that is Vi cos theta minus theta V minus theta I equals to into Vi, obviously, because cos theta V minus theta I is 1. So I mean kilowatt equals to kilovolt amperes. If I write this thing in complex power format, 22 is the apparent power, okay, and angle would be 0. So if I write this thing in this formula Vi conjugate, and let's just say the angle here, sorry, the voltage here is 220. So I'm 220 angle 0 just for easiness sake. So I conjugate is 100 angle 0 and I just invert the sign of 0, that will still remain 0. The current here is 100 amperes to provide 22,000 watts of power at 220 volts. Now we take the case 2. We have the same load, 22 kilowatt. I mean that's actually doing the work here, but the power factor is 0.5 lagging. That means it has a huge inductive component in this load. It has a resistor and it has an inductor as well. So I mean that's why, I mean, due to the very large inductance, the power factor is now 0.5 lagging. So if power factor is 0.5 lagging, power factor angle is cos inverse 0.5, that is 60 degrees. I'm going to write plus here because lagging is here, and this 60 degrees theta v minus theta I, and the current angle is less than the voltage angle. So if I use the power factor equals to average to apparent power ratio, I get the apparent power is 44,000 VA, or if I write this thing in the polar form, 44 is the apparent power, angle is 60, and 22 plus J is 38.10. I mean 22 kilowatts is the same here, but J 38.10, it was not here in this because it has a unity power factor. Here is 38.10 kVAR, that represents the energy being exchanged by this very large inductor and the source. So that means if I compute the current 44,000 angle 60 divided by 220 angle 0, I get 200 amperes. That means at lower power factor, more current is required to deliver the same amount of real power which does the actual work. So that means that reactive and quadrature power here, this thing, represents the energy exchange between source and the load reactance. So what is actually going on here at that the utility supplies, they do not like the loads at very low lagging power factors. The reason is to supply the same amount of power, they have to transmit a large amount of current through the transmission line. I mean here the current is 100 amperes. In this scenario the current is 200 amperes, but both of these currents are doing the same amount of work here, 22 kilowatt and 22 kilowatt here. That means that due to large currents being required by these low lagging power factor loads, they increase the line losses, the amount of power being absorbed by the line. Because the billing is done at the consumer end, the source or the utility company has to supply a larger amount of current for lower power factors, away from the unity obviously, to deliver the same amount of power, even though they are making up a large power, but they are only built for this thing. 22 kilowatt. That's why the utility companies for industrial consumers, not for residential consumers, because they are like 4 or 5 kilowatt consumers. For industrial consumers who are consuming the powers in terms of hundreds of kilowatts and in maybe in hundreds of megawatts, they have another meter known as power factor meter. So if the power factor is let's say less than 0.85, I think that's the I mean, you have to check the KE tariff, the Karachi electric tariff. If it's less than certain value, let's say it's less than 0.85, they are going to charge you more per kilowatt hour. I mean, they could have reactive power meters as well. They could have power factor meter as well. To if they say that the power factor, I mean, if they can measure the power factor to be less than certain value, they are going to charge you more per unit of energy, because they have to transmit a large amount of current to the load, thereby suffering large line losses on part of the utility side, because the consumer is only going to pay whatever is being billed at their premises, and they are getting 22 kilowatts, but they are getting a very large amount of current. That's why industry consumers either have a power factor meter, or they could have the reactive power meters, so they can figure out the power factor. And one last thing, leading power factor actually lead to increase in voltages, so utilities actually do not like that to happen. They can if that's a scenario, they might use some kind of a shunt inductance to make the power factor from leading to slightly less than unity. So coming back to this example, and let's say we have a simple example when connected to 120 volts 60 hertz power line. Here in our country, the voltage is 220 volts RMS as 50 hertz. Do not mix it up. Okay, 60 hertz is given in American books, but here it is 50 hertz. A load absorbed of 4 kilowatt at a power factor of 0.8, but we want to increase its power factor to 0.95 lagging. So obviously we need to have some capacitor right next to it in parallel. We do not want to change the load because it might be some kind of a motor. We cannot change that motor. We can actually attach a capacitor so that the overall power factor goes from 0.8 to unity, or maybe to 0.95. We just keep it slightly less than unity to avoid accidentally going into the leading power factors, because that might increase the voltage and that might mess up with the excitation of the synchronous generator. Okay, so if I mean, you're going to see this detail in some other course. If power factor is 0.8, so we just figure out 36.87, and if theta n is the phase difference between voltage and current, we obtain the apparent power from the real power and power factor, as because apparent power is the power factor is the ratio of the real power to apparent power. So we just figure out the apparent power is 5000 VA. We can just write it in terms of, I mean, the quadrature power is apparent power of sine of that angle, the power factor angle here. That is 3000 VAR. I mean, I could have written as 5000 angle 36.87, and I'm in polar form and in rectangular form, that would have been 4000 plus J 5000. Okay, and sorry, that would have been 4000 plus J 3000, because that's the reactive power. If the power factor is raised to 0.95, that means we are not changing the load here. We are not changing the real power. That means that theta 2 is going to be cos inverse of 0.95, that is 18.19. So here originally the angle difference between voltage and current was 36.87. We want to have a capacitor so that the angle difference or the phase difference between voltage and current reduces from 36.87 to 18.19. So real power has not changed because we are not changing the actual load. We cannot change the motor. We can only install another capacitor in parallel with it. So its new value is, I mean, the new value for the apparent power is P divided by cos theta 2. I mean, this real power divided by 0.95. I mean, what we want is that this load, this overall load has the real power of 4000 watts given here, but now it has to be the imaginary part, or the reactive power part has now to be J 4210 volt amperes. We want it to, I mean, sorry, not J, the apparent power. And if we, sorry, if we just take the, my mistake, let me recap it again. we want the power factor to be raised to 0.95. We take cos inverse of 0.995, that is 18.19. That means we want to reduce the angle between voltage and current from 36.87 to 18.19. So I mean, if we want it to be unity, we can make the angle to 0 degrees. Okay, so real power has not changed, but the apparent power has changed. So the new apparent power is P divided by cos theta 2, that is 4210 VA, and the reactive power is, I can just write this thing as 4210 angle 18.19. If I write this thing in rectangular form, that would be 4000 plus J 1314. So the original reactive power was 3000. We want it to be reduced to 1314. That means we have to use a capacitor. We 3000 was the original reactive power. We want it to be reduced to 1314 VAR. So the capacitor we want has to deliver the reactive power of Q1 minus Q2 equals to 1685 VAR. So that means if we connect a capacitor right next to it which has the reactive power of this thing, it will reduce the overall complex power, reactive power from 3000 to 1314, because this thing is actually in negative. Okay, reactive capacitors have negative reactive power and the inductors have positive reactive power. So C equals to, using the formula which is being given in your book, QC divided by omega V square. So the voltage is 2 pi 60 hertz into 120. For in our country that would have been 2 pi 50 into 220 square, and that would have put the new value for the capacitor here. So capacitors are normally purchased by voltage they expect to see. So in this case the maximum voltage is not 120 volt, it has to be, because this is an RMS value. The peak value is 120 into root 2, so that would be 170. If you are talking about a 220 volt RMS line, you have to use a capacitor which can see up to 311 volts. So obviously you are going to use something known as like maybe a 350 or maybe a 400 volt capacitor.